we go. So for tan, we can have the A and the B and the C and the D transformations just like for any other function. But because it's not a wave shape, because it's not sinusoidal, A goes back to being a vertical expansion or compression. It's nothing to do with amplitude because a tan function doesn't have amplitude. B still affects your period. It's a horizontal expansion or compression, so it affects your period, but your period for tan is pi, so we would divide pi by B rather than 2 pi like we do for sine and cosine. C is not a phase shift because we don't have a wave, so we can't shift the phase. It's a horizontal shift, and D is a vertical shift. Okay? Now the order for graphing, we still have flexibility in the order because it's a periodic function, but my suggestion would be to figure out where the asymptotes go first, and then we know the basic shape of a tan graph, so we're going to put our points in, and we'll talk about that. So I'm going to do some examples with tan graphs so you can see what I mean by the shape. Okay? Questions for me about tangent functions? So the first one we're going to graph is the one from your worksheet, the first one on the worksheet, which says y equals tan half x. So the only change to our normal tan function is that now our period is what?
Double.
Is doubled. So we have a period of 2 pi. Okay? So let's think about the scale of our graph. And what have you guys got for scale? Maybe I'll stick with that same scale. So you're just going up by ones? Okay, so 1, 2, 3, 4, and down 1, 2, 3, negative 4. And then you've got 4 spaces for pi. Okay, 1, 2, 3, so pi, negative pi. Okay, so it's the same as yours. So let's think about where the asymptotes normally go for tan. Normally, the very first asymptote is where? Yep.
Pi by half, pi by 2.
Pi by 2. So we normally have asymptotes at pi by 2 and negative pi by 2. So I'm not going to mark it in, but here and here. I'm not going to put asymptotes in because that's not where they're going to be. And notice that they are pi apart from one another. Okay? Yep.
They double.
They're going to double because we have expanded by 2, so our period is expanded by 2. So instead of having our asymptotes at pi by 2 and negative pi by 2, we want to double those. They're going to be at pi and negative pi. Now these are actual asymptotes. These are not like we were using before, guidelines. Okay, so today I'm going to use green for asymptotes because they would stay on your graph. Okay. Now, the rest of the graph for tan is quite easy if you can remember the shape. Remember the shape is kind of snakes like this. I hope it shows up in the video. I think it does. Okay. The 0 is always right in between the two asymptotes. And that's not going to change. So we're going to have a 0 right there. The other part that stays the same is that right in between the 0 and the asymptote, we have a point that is a y value of what? Look on your graph on page 411 or 511. Right in between the two, y equals. Can anyone figure it out? Not x, y. What does y equal? 1. Y equals 1. Right in between, we're going to have y equals 1, and right in between here, we're going to have y equals negative 1. And so that tan graph is going to look like this. Now that y value will change if we have changes to the y value here, an expansion or compression or a vertical shift up or down. But for this graph, the only change was the period, so the only thing that changed is where the asymptotes are located and then how far apart these points are from one another. Okay? So if you look at your graph on page 511 and compare it to this one is just expanded horizontally by doubling all those points, by making them twice as far out from the y-intercept as they were before. Okay. Now we can put in more periods of this graph by just adding in some asymptotes. So that's pi. If I go out another another 4, I'll be at 2 pi. So I want to have my asymptotes be 2 pi apart, so I need to go another 4, which I don't know if you have room on your sheet. Okay, but out here I would have another asymptote. And same in the other direction, I would have another asymptote. So mine's slightly off the graph too. Oh, it doesn't do very well on the side. Just has some serious resolution issues on the side of the graph. Okay, so I have that. The 0 is going to be right in the middle, so you can put the zeros in. They're going to be at 2 pi and negative 2 pi, which you do have room for on your graph. Okay. Yes, Jack?
Can you explain again why we have asymptotes?
Yeah, just give me 1 second here. And then in between the 0 and the asymptote, we'll have a +1 and a -1. So for you, you're only going to be able to draw that half of it. And over on this side, you could draw that half of it. But that's the shape of it. Okay? Okay, so remember that tan is opposite over adjacent. And so if we're on a unit circle anywhere here, where this is the point xy on the unit circle, so the radius is 1, then the opposite side is here and the adjacent side is here, and so the tan of that angle here is the tan that we're talking about. Okay? And remember, on the unit circle, y is sine theta and x is cos theta. So we are going to have asymptotes wherever the denominator is equal to 0, because those are non-permissible values of the variable. And that happens, so wherever cosine is 0, we have asymptotes. And so that's where these are. Now, this, of course, is sine half theta over cos half theta, because we've had an expansion horizontally. And so those zeros got expanded horizontally, which means the asymptotes got expanded horizontally. For a normal tan theta graph, yes. They're at pi by 2 and negative pi by 2. Okay? All right, further questions about that? So let's try the next one. Search. Okay, so I'm going to set mine up the exact same way as yours. 4, negative 4, pi, negative pi. Oh, I went too far over there. Okay, and our new function here, if I could look at yours, Will, is y equals 2 tan x. Okay? All right, so what's going on here? Vertical expansion, right. So with a tan graph, we don't talk about amplitude because we don't have a wave. But it's a vertical expansion by 2. So that means that, are my asymptotes affected? No, because those are horizontal issues. So the asymptotes are still going to be at pi by 2 and negative pi by 2. And then they're every pi apart. So if I count over 4, I'm going to have another set of asymptotes. So you can put in another set of asymptotes there. And over here, I'm going to have another set of asymptotes. So we can label those. That's pi over 2. That's 3 pi by 2. Remember, they're every odd pi. Okay. And they go on forever. I'm just going to stop there because I think you're going to run out of space on your graph. Okay. Okay. Now, are the zeros going to be affected by a vertical expansion? Zeros of the graph are at y equals 0. So if I multiply that by 2, I'm still going to get y equals 0. So the zeros are all in the same place, here and here and here. Halfway between the asymptotes, we have zeros. Okay, so if you can figure out where the asymptotes are, you can figure out where the zeros are. You don't even have to think too hard about it. It's just halfway in between them. Okay? Now, halfway between the zeros and the asymptotes, we are going to have y equals 1. Except in this case, y equals 1 becomes y equals 2. Because it's a vertical expansion by 2. So we'll have a 2 and a negative 2. 2 and negative 2. 2 and negative 2. And the pattern would repeat forever and ever and ever. Okay, so what's the domain going to be here? The domain's going to be where the asymptotes are, correct? And so where are the asymptotes? Every odd pi. So you know how to make that. But if it weren't odd pi's, if it wasn't something easy like that, then my advice is to take the very first positive asymptote, which is located at pi by 2, and then you notice that they repeat every, how often? Pi. So n pi. Okay? So some people prefer to do that 2n plus 1 thing, but the thing about the 2n plus 1 is it doesn't work every time. It works for a basic y equals tan x graph, but it doesn't work if we're going to shift things around left, right, or change the period too significantly. So an easier way to do it is to start with your very first asymptote and then add n times however often those asymptotes repeat. So n times the period. Okay? What's the range going to be here? All real numbers, right? The range doesn't change. Okay, Paige, is that all right? Okay.